Okay, today, section 4, line 4, iterative solution of linear systems. The second topic, the Jacobi method. Jacobi method. The linear systems here is large and sparse. Okay. Large and sparse. Okay. We consider in this section, line 4, we consider iterative methods of the following form. Okay, we consider iterative methods of the form. Okay, this form. Yeah. T matrix. UK, the vector we obtain at iteration K. So a matrix times a vector. This is a vector. Then plus C. C is a vector. Then this is a U K plus 1. Where T is a matrix, n by n matrix. What is K? K starts with 0, 1, 2, and so on. To run these iterative methods, to run this iterative equation, we need initial vector, right? Initial vector, yeah. Initially, we assign a vector, say vector U0. For the convenience of my presentation, let me give a name to the matrix T. Okay. What is the name? Iteration matrix. Yeah, call this iteration matrix. Yeah. In section 4, we consider methods of this form to solve linear system. Yeah. Solve linear system. To make this iteration method scheme, okay, useful, we need 2 requirements on this scheme. Okay, yeah. Requirement. Okay, we require. Okay. Yeah. Number 1, this iteration scheme should converge. Okay, yeah. SK iteration number approaches infinity. Okay, yeah. UK should converge. Okay, converge to some vector U. Converge. If diverge, then this scheme is useless for the solution of linear system. We want to solve this linear system. Okay. Second. This iteration scheme should converge, yes, and also should converge to the solution of the linear system. Otherwise, use this, right? We want to solve this. Then this iteration scheme converge to some vector. The vector is not the solution of this linear system. Then this iteration scheme use this. Not useful. Okay. So yeah. We also require, U should be the solution. Okay. X star by X star, I mean the solution of the linear system. Hey, here here is two theoretical results about an iteration scheme of this form. Okay, here. You can find these results from the book. Philip. I call it Philip number one. Okay. Then this law, this is a matrix law. Be a lateral matrix long. Okay, what it means? Lateral matrix long. Okay, lateral matrix long. What is the meaning? Okay. The meaning is here. Okay, yeah. Okay. Then this be any vector long. Vector long. Say too long, right? Too long. Too long definition is this, right? A vector. How to compute the too long? Yeah. Component one take square. Component two take square, and so on. And take square. One long, right? One long. One long. One long is component one take absolute value. Component two take absolute value. Then make sum. Yeah. This is one long. We also have infinite long, right? Infinite long. Infinite long means absolute value on component one, first component, absolute value, second component, and so on. Yeah. And then the largest maximum, okay, maximum. This is a infinite long. Let this be any vector long, okay, and then S sphere, okay, sphere, sphere. Let S be the unit sphere. Sphere. What unit sphere? Okay. Any vector. Yeah. In Rn. Yeah. The long is equal to 1. Yeah. Unit sphere. Yeah. Okay. Now, this matrix long is defined as A times V. Yeah. Vector long. A times V is a vector. Now take long. What is V? V is from this sphere. Okay. Okay. Take maximum. Yeah. Maximum. Maximum over all vectors from the sphere. Sphere. Okay. Yeah. A matrix long defined in this way is called a natural matrix long. Matrix long. Yeah, this is a very mathematical. Okay. Okay. Now, if this the matrix T in this iteration scheme, okay, if T is a matrix, yeah, apply this matrix long to T. If less than 1, then guarantee then the iteration scheme, okay, the iteration equation or equation, yeah. Let me give a name, say star, okay, star. Guarantee will converge to some vector, guarantee to some vector, okay. Guarantee, yes. So whether is equation converge, have a check the norm on T. If the norm less than 1, guarantee. Okay? Number 1 is guaranteed. Number 1. Right. And how fast the convergence and UK minus U, okay? Yeah. The vector long less than T long K times U 0 minus U. Yeah, so fast. So fast. Yeah. T long, the long of T less than 1, say 0.5, then 0.5 to K, okay, to converge very fast. But this result doesn't say anything about number 2, okay? Yeah, just converge to some vector U. It doesn't say anything about whether U is the solution of the linear system. B, second result, okay. Second result is stronger, okay. Yeah. Okay. The iteration scheme or equation scheme start converge converge for any initial arbitrary give a vector as an initial vector, okay? For any initial vector, if and only if and only if, yeah. Rho T, spectral radius of matrix T. What it means, spectral radius, yeah. Yeah, rho T is equal to the largest eigenvalue in absolute value, yeah. The largest eigenvalue of T in absolute value. Rho t is called, give a name, a spectral radius. Spectral radius. Yeah, that's next one. A general matrix eigenvalues are usually complex. Okay, yes. Eigenvalues. In absolute value, which eigenvalue is the largest? In absolute value, take absolute value. The complex number, take absolute value. I believe, yeah, is eigenvalue. Yeah, absolute value may be the largest. Yeah. From 0 to this point, the distance is called spectral radius. Yeah. If you draw a circle, then the circle contains all the eigenvalues, and the radius of the circle is rho t. This scheme converge for any initial guess if and only if the spectral radius of t less than 1. Okay. Yeah. Compare all the eigenvalues of t. Take absolute value. If the largest absolute value less than 1, guaranteed. Okay. This scheme converge to some vector u. Okay. To some vector u. How fast? Okay. Further. Okay. Okay. In this case, which case? Yeah. The spectral radius less than 1 in the case. Okay. How fast? Okay. Yeah. UK minus U. Okay. Less than roughly is some number times spectral radius to k times k to n. What is n? The size of the matrix. Yeah, t. Yeah, t. Yeah, n. Yeah, size of the matrix. K iteration number. N doesn't change. The matrix is a billion by billion, then n is billion. It's basic. But k is a 0, 1, 2, k is changed. Times, okay, initial u minus the u by u. I mean, yeah, this scheme converge to u, suppose. What is C? C, constant. Where? C is a constant. Depending on initial guess, U0, and the norm, okay, that you choose. It doesn't depend on K, okay. K doesn't depend. Yeah, let me show you one example, okay. Yeah. Especially part B. Part B is very strong, okay, if and only if the scheme converge to some point for any initial guess, then T is which is the largest eigenvalue in absolute value less than 1. The reverse also true. Let me show you examples. Say, take a look. I want to solve the following linear system. Okay. Example 1. Example 1. Okay. Consider is linear system. Now let me design an iteration scheme to solve the linear system. Okay. Let me see. Coefficient matrix is 3, 1, -1, 1, -4, 2, -2. Yeah, 5. Coefficient matrix. Right hand side B is 3, -1, 2. Yeah, right hand side. The unknown, right? Unknown is x1, x2, x3. Unknown. Linear system, right? Ax is equal to b. Hey, now let me I want to design, okay, a scheme, okay. Let me design a scheme in this way, okay. Write x as a matrix, identity matrix times x. It is x, right? Then is x minus ax plus ax. Okay. So this is ix minus ax plus b, because a times x is b. Okay, now I minus a x plus b. Okay, now let me based on this equation, let me define my iteration. Okay, yeah, here. Left side, okay. U k plus 1. Yeah. Right side. I minus a u k. Then plus b. Yeah. Yeah. Based on this equation, let me define my iteration scheme to be this. Okay. Yeah. How to construct an iteration scheme? Just up to you, right? Yeah. Good or not? Okay. If the scheme, okay, this scheme converges, okay. I don't know whether it is converged or not. I need to have a check the conditions. If this scheme converges to say some vector, okay, then this vector must be the solution of the linear system. How to see? Okay, if this scheme converges to U, now let me let k approach infinity. Okay, on the both sides. Then left side is U, right? K approaches infinity. Then this is I a U, right? Has been. You agree? Now U distribution, yeah, distribution U times I, then minus a U is B, right? Yeah, distribution. You agree? Now cancel U on the both sides, then zero vector A, U, B. Yeah. All right, now from here, I move negative A times U to left side, then AU is B. So U is the solution of AX is equal to B because U satisfies this equation. Right. If this scheme is convergent, then the vector U must be solution of the linear system. Now, the next question is whether this scheme is convergent. Okay, it's convergent. Let me compute the spectral radius of this matrix. Yeah, this is T. Yeah, T. This is T, right? Yeah. If this T spectral radius is less than 1, then guaranteed by this sphere. Yeah, happy guarantee. This iteration scheme converges for any initial guess. Okay. Okay, now let me compute. Okay, computer. Okay, not by hand. Yeah. Okay, now compute. Okay, P is I minus A. Okay, what is A? Coefficient matrix. Then I identity matrix. Then easy to see. 2, -1, 1, -1, 5, -2, 2, 1, -1. Yeah, yeah. Identity matrix minus coefficient matrix is this matrix. Now compute all the free by free matrix has free eigenvalues. Compute the free eigenvalues. Then take absolute value. The largest absolute value of the free eigenvalues is low. Okay, 4.9675, greater than 1. So that means that this iteration scheme doesn't converge. Yeah, greater than 1. Yeah, this number greater than 1. So the iteration scheme doesn't converge for all initial guess. In fact, arbitrarily pick a vector, numerical data shows that doesn't converge because doesn't converge. Actually go up to infinity because you see this is greater than 1. As k approaches infinity, this part approaches infinity. So not a good scheme. Okay. Yeah. Hey, now we define my scheme. Okay. Okay. Then I drop this scheme. Okay. Now let me define another scheme to solve the linear scheme. This is not good. Okay, not good. Okay, now here as second scheme. Okay, solve the first equation for x1. Okay, solve for x1. Move x2, x3 to the right side. Divide the equation by number 3. Then I get 1 divided the equation by 3 divided by 3, 1. Minus 1 over 3 x2 plus 1 over 3 x3. Right. Solve the equation for first equation for x1. Right. Move to the right side. Then divide the equation by 3. Then I get this. Okay, now second equation. Solve the second equation for x2. How to do that? Move x1 to left side, to right side. To x3 to right side, then divide the equation by -4. Right? Then 1/4. Move 1/4 x1. Move 1/4 1/2. Okay, yeah, x2 x3. Right? Yeah, you can sit down to have a check. So the second equation for x2, then move x1 x3 to right side, divide the equation by -4. Then I get here. That equation, solve the equation for x3. Yeah. -2x1 to right side, x2 to right side, divide the equation by 5. Then x3 is 2/5 plus 2/5 plus 1/5. 1/5 x2. Hey, now let me define a new iteration scheme. Okay, left hand side I will replace left hand side by u k plus 1. Okay, yeah, left side. How about this part? This part is t times u k. Okay, what is uk? Then replace x1 by uk. First entry of uk. Yeah, this is the third entry of uk. Then plus c. What is c? Yeah, c is this vector. Yeah, this vector. Yeah. Where? Okay. Where? T is the coefficient. Okay, coefficient which is 0 because low x1. So 0. x2 1 -1/3. x3 1/3. Yeah. Coefficients of first equation 0. Yeah. Coefficient of second equation 1/4. 0 1/2. Yeah. And then 2/5. 1/5. Then 0. Right? Okay. Yeah, the t. How about c? C is this vector. 1/4. 2/5. Yeah, this way. This is a new scheme. Okay, new iteration scheme. Now, whether this scheme is good, compare eigenvalues of these iteration matrix. Then take absolute value and see what is the largest absolute value. It turns out that this time, okay, rho of this t, is 0.5, less than 1. So this scheme converge to some vector in converge to some vector u. Okay, say take k, let k go to infinity, then left side to u, then t u plus c. Okay, then it turns out that from this equation we have au is equal to b. So when this scheme is convergent, the vector must be the solution of the linear system. Yeah. Spectral radius less than 1, guarantee. Yeah, guarantee. the scheme converge. How fast? Actually, super fast. 0.5 to K. When K, go to infinity, this factor drop to 0 quickly, very quickly. This scheme converge very fast. So how can construct, how to design, how to define a scheme? Just up to you. Just up to you. This is a topic 1. Okay. Now second topic. Jacobi iteration. Jacobi method. Jacobi. Topic 2. The Jacobi iteration. Iteration scheme. Scheme. Iteration scheme. We want to solve. We want to solve. Ax is equal to b. Ax is equal. Now define a scheme. In detail. Write out this linear system in detail. This is a A11 x1, A12 x2, A1n xn is B1, right? A21, A22, A2n, B2, AN1, AN2, ANN. I want to solve the linear system. Now, how to define a scheme? How about use the idea here? The idea here. Because in this example, this idea works well. How about use the idea? Now here. Solve first equation for x1. X1 is move everything to right side. So B1 over A11, right? Divide the solve for x1, then divide the move everything to left side except x1. Divide the equation by A11. Minus A12, A11, x2, minus A1n, A11, xn. From the second equation, solve the second equation for x2. Then we get x2 is B2, A22 minus A21, A22 minus A23, A22, x3, and minus minus A2n, A22, xn, and so on. So now replace the x on left side by UK plus 1. The x on the right side by UK. Then I have iteration scheme. this is a entry wise derivation. Okay, if I use matrix, then the scheme is easy to understand. Okay, the structure is simpler. Yeah. How about let me write in matrix form. It's easier to present the scheme. Okay. Right matrix A, coefficient matrix is okay. Split the coefficient matrix into L. L means lower triangular part. This is a strictly lower. Yeah. Doesn't include the diagonal. The main diagonal row. Okay. L strictly lower triangular part of matrix A. Yeah. I will show you example. Then pass diagonal part of A plus strictly upper triangular part. Say for example, say if matrix A is 3, 1, -1, 1, -4, 2, 5. Okay. Now, how to cut this matrix? Yeah. Okay. Write the matrix as L lower triangular part. Lower triangular part, the part doesn't include the main diagonal line. So 0, 0, 0, 1, -2, -1, 0, 0, 0. Yeah. This is a F. F. Okay. What is the diagonal? Yeah. Diagonal. This is a D. Okay. What is U? Okay. U is upper triangle. The upper triangle doesn't contain the main diagonal. So 0, 1, -1, 0, 0, 2, 0, 0, 0. Any matrix can be split into LDU. This form. Okay. Now, after I split A into LDU, then linear system is L D U X is B, right? Right. Now distribution. Yeah, distribution. Then I get L X plus D X plus U X is B. Now, solve the first equation, solve for x1. Second equation, solve for x2. Last equation, solve for xn is equivalent to move L U to the right side. Same. Okay. B minus L X. Minus U X. Same. Okay. Now move D to the right hand side. How to move D to the right hand side? Multiply the equation from the left by D inverse. Okay. D inverse B L X U. Yeah. Okay. Now Alright, let me simplify, okay, simplify. X D inverse B, yeah, B, yeah. Then plus D inverse negative L X U X, right? Distribution. Distribution. How about take XR? Yeah, take XR. Okay. Take XR. Yeah, take XR. Then take negative sign R minus. Yeah. 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 So this is okay. This is X is D minus D inverse L plus U. Okay. Yeah. To get this. Yeah. Actually, same here. Exactly this. Okay. This. Hey, now Jacobi scheme. Jacobi. 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 Yeah. Jacobi scheme. Iteration scheme. Okay. Replace the x by u k plus 1. Then okay. What is matrix T? Yeah, matrix T. Yeah. This is a negative D inverse L plus U. Replace this by U K. Then plus, yeah, this is a vector C. Yeah. D inverse D. This is a T iteration matrix T. This is a C vector C. Yeah. This scheme is called Jacobi scheme. Whether this scheme is convergent, you need to compare, check, convert this scheme is convergent or not. Have a check. The matrix T. Compute all the eigenvalues, take absolute value, and see whether the largest eigenvalue less than 1. If less than 1, yeah, sure, this scheme converge. If larger than 1, diverge. The problem is, usually the linear system in practice is super large. Building. How to compare all the eigenvalues? Impossible. Compute all the eigenvalues, then take absolute value and have a check the largest eigenvalue. Impossible, okay? So we need to think about the other way to have a check this, okay? Yeah. We continue this topic Wednesday. Hey, suppose I give a talk, right, in your class. The room is upstairs, right? 305, right?
308.
308. Okay. I go up.